Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems, and that's this video here right now. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And then finally, we'll do some fuzzing techniques. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
So the first thing I really like to go through with my students, and we won't spend tons of time on this because I'm sure you're all pretty well versed in this area, but I like to talk a little bit about numbering systems. So as students come into the class, they should have a good background in C and ideally some assembly as well. And from there you can help them build up the skill sets in RE. But part of this is identifying how data is represented. And we know on a computer, what numbering system do our machines really care about?
Base 2.
Binary, right? Base 2. So if I ask you this question, we can all kind of laugh about it. What number is this? 2 in binary, 10 in decimal. What would it be in hexadecimal? 16, right? So the context of what we're looking at starts to matter quite a bit. So I like to have my students be able to understand and see some of these like smaller numbers, be able to translate between the different data formats quickly. Because if we find something that might be of interest to us, if we can identify what that is in our head without having to open up a calculator, that makes our lives a little bit easier. So we call those numbering systems a radix, and a radix is basically just a way of representing data in a different number system. So if our computers deal 100% in binary, why do we have numbers represented as decimal? 10 fingers, 10 toes, most of us. That's the number system we use in our day-to-day lives. That's easy for us to do. So I bring up the question of why would we ever represent data in hexadecimal? Because hexadecimal is not something I use as a person. My computer uses binary, but a lot of the tools and output that we see ends up in hex. So why is hex so important for us to know? But it makes basically a large amount of data represented in a smaller thing to see. It's easier to type, easier to read, right? Instead of reading out long streams of binary, we can look at that same thing in hex. So if I were to teach class and have students come in and be able to translate between some of these basic things, I would probably request that they know how to translate between binary and decimal and hex for at least like this first 16 numbers. So if we're dealing with 4 bits of binary, just for fun trivia thing here, what is that data type size called? 4 bits. A nibble, right? A half a byte, like a small byte would be a nibble. So that's kind of what I work for on that. It's important to know too that we're dealing with all positional numberings. So if we look at the number systems that we use and what our computers use, the actual position of that number doesn't really change the value of it. So if we look at the number 20, that's basically saying I have 2 quantities of 10. right? The 2 is still a 2, but because it's in that tens place, that defines on how much data that is. The only like non-positional numbering system that we have is Roman numerals, where if we have a 1 as a 5, an I as a 1, a V as a 5, if I have VI, what is that number? 6, right? It's not 51. So it's a little bit weird to see that kind of stuff there. So let's start with converting a number from, let's go just decimal to binary. So let's start with a 2-digit decimal number, 26. So if I want to convert 26 into binary, how are we going to do that? So if we use this concept of we're looking for what is a whole number, does it have a remainder, we can use those two things to test student knowledge on can they do this process right. And I'll show what I mean by that. So if I take 26 divided by 2, what does that equal? 13 with a remainder of 0, right? So I'll just make this 13 with a remainder of 0. If it has a remainder or not, that's going to be our first place in binary. So this binary sequence to represent 26 is going to end in 0. What is 13 divided by 2? 6. Is there a remainder? There is, right? So we're going to have a remainder of 1. And we take 6 divided by 2. What is 6 divided by 2? 3. Is there a remainder? Oops. What is 3 divided by 2? 1. You guys are making me nervous. 1 with a remainder of 1. And if you wanted to, just for completion, here we go. What is 1 divided by 2? 0, remainder 1. And that should be our binary sequence, right? So a question I would ask my students, and something that you guys will see in the CTF, is I might say, what was the third number that we divided when trying to convert from decimal to binary? Like if 26 was our first, 13 was our second, 6 was our third, their answer to that question would be the 6 there. So by doing it this way, they're not going to be able to see that by using a calculator. Like if we opened up the Windows programming calculator and just did the conversion, they'll see the binary sequence, but they won't see the steps in between. So it is a long way of doing things, but it's an interesting way to kind of really check someone's knowledge on it. Obviously, when we're dealing with these tools, we're going to see a lot of stuff represented in hex. So the bytes of our programs, the machine instructions that we look at, are going to be always present in hex because we can see those in their individual bytes. But our tools are going to help us translate that data into more meaningful things. Another kind of interesting thing that you can do with your students, instead of just looking at my examples of like, give me a number and we'll convert it, is actually seeing that conversion happening in like real software programs, stuff like that. So go ahead and open up your, let's go to your Kali virtual machine and open up a terminal. And let's go into your desktop, into the Git folder. And if we run something like ls-l, that shows us the file permissions and folder permissions for everything I have in that directory. So the file permissions in Linux are represented by octal numbers. So if we look at this permission set here, since this is a file, we don't have the D on the left-hand side, right? D for directory. So if this is just a file, we see the different permissions here. If we group them up by 3s, we have read-write for something, read for something else, and read for the last piece there. Does anyone know what those 3 different groupings are? Any Linux masters in here? User, group, and other. So the user would have read-write permissions, the group would have read permissions, and other, or basically everything else, would have read permissions. Well, those are just represented out by binary numbers here. So I'm going to open up a text editor. And that was the file permissions that we saw before that. So what we had here was user, group, other. So basically if that file permission is turned on, like in the context of user, read is turned on, write is turned on, what's the last piece? Execute is turned off. So this would be the binary representation of that permission. What would that be in decimal? Would be 6. Right? So we can give students like a directory of files, have them convert between those types of things too. Where this becomes more important for us is if we wanted to like actually change permissions on a file. If you're familiar with the chmod command, like let's say we wanted that user to be able to execute the PDF, which why you would do that, there's no practical reason, but if we wanted to give that user execute permissions for the PDF, how could we do it? So there is a way where we can just do like a +X, right, to add execute permissions, or you can define them by the decimal numbers there as well. So if I wanted to give that user execute permissions, their permissions would need to look like read, write, execute, or binary 111. What would that equal in decimal? 7. So when we give that command there to change them for the user, we also have to give the permissions for the group and for that other section. So we need to actually convert these last couple as well. So what would 100 be in? Would be decimal 4. So if we want to change these permissions to read, write, execute, read, we'd have 774 slides.pdf. Now if we do an ls-l on that, I messed that up because I did 774. You all told me it was 744. That was the first test of the day. We didn't pass. But anyways, if we're kind of okay with that, any questions? Okay, so it's again, not something super specific to RE, but just another way that we can really kind of confirm that we know how these different numbering systems all tie together and work. Cool, so that's kind of a just exercise I might use by that. Next thing that we need to know is that we can actually divide all of these different numbering systems the same way that we can do things with decimal. And this actually has a little bit more context when we get into reverse engineering and start dealing with addresses. When I look at a memory address in any of our RE tools, we're going to see them, if it's a 32-bit program, in 4 bytes of hexadecimal. And typically what we'll find is that variables and different functions are referenced by an offset from a base memory address. So if I know something is 20 bytes away from the top of the function, in my head I should be able to really quickly be able to do that math and find out what memory address should I find that thing at. And so the addition, subtraction, divisibility, all that stuff works in hexadecimal and binary the same way it does in decimal. So it's kind of a cool thing. Right, if I take hexadecimal 1230 divided by hexadecimal 10, it just comes out to be hex 123. And it sounds like a simple concept, but I think that gets lost when we switch into numbering systems because we're thinking like, these are 16 possible values, like does that math all still work? It really does. So if I took 1337, 000 divided by hex 1000, same thing you do in decimal, just chop off those last 3 decimal points, get same thing. And then for binary, which to me was kind of the mind-blowing one, works the same way too. So if I took binary 1000101000 divided by binary 1000, chop off the last 3 zeros, you get your binary number. And so you might be thinking like, why are we dividing? This doesn't really necessarily matter, but again, it's about finding those offsets from something. When we load up a binary file in any of our tools, they're typically going to have a base memory address. So for those of you that have done some reverse engineering before, if you open up, let's say, a Windows binary in your debugger or your disassembler or whatever tool you have, what is the base memory address typically? It's typically 400,000. So it's like the very lowest memory address that you're going to have. You might have a function at like 400,500, right? It's always going to be above that. But it's all about having a understanding of how those memory addresses are related to each other and how far away things exist. Prior to like Windows XP, so we're talking Windows NT, the base memory addresses for those were 10,000. So if you're dealing with really old applications, you'll see a very low base memory address. Newer applications are all going to be a base address of 400,000 for that. So it's just kind of interesting things of that. But it's how those files are all laid out. We all remember the good old days of Windows, right? Okay, so question for you all. So we're going to kind of get into a little bit more technical things here in a little bit, but I want to kind of set the stage, make sure that we have a baseline knowledge. When we say the words, we're all in the same understanding of what we're talking about here. So two words that are going to come up quite often are disassembling and decompiling. So can someone tell me what decompiling means? Right, so if I wrote a C program, I compiled that C program. In the process of decompiling it, I'm trying to get back, what does the source C code look like? If I'm disassembling something, what am I doing? Trying to get the assembly for the opcodes? Right. So if we talk about the compilation process or just writing software in general, we write software in, let's say, C. C is a mildly friendly language. Some of us might hate C, but like it's a reasonably usable language. Right? There's words like printf, scanf, like things that we understand as people. When we compile that C code, so if I run that through GCC or I run it through Visual Studio, what is the output of the compilation process? It's, yeah, the binary, like the instructions that your processor wants to look at and execute. When we disassemble something, we're taking it from those processor instructions in binary, moving it back into assembly language, which kind of sits between C and the machine code. It's less friendly for us, but if we practice with this stuff, we can get an idea of what things are actually supposed to be doing. So typically what we're going to find is that we can always get the disassembly of something. If it's going to run on your processor, like it's an executable that can actually run on that machine, your machine has to be able to read those instructions. And just by the nature of that, we can convert those instructions back into assembly. So we can pretty much always get that. But a question I have, yeah?
So is there a difference between things like Java or .NET when you have a...
Yeah, so that's actually a really good question. So we have what's called managed and unmanaged code. And it kind of depends on like the language you're working with there, which I actually have a slide on that. But I like the question though. So when I'm dealing with C programs, we talk about those being as unmanaged software. So when I compile that, the operating system can execute the code in there directly. Has everything that it needs to know about how to run that C program. When I'm dealing with something like C#, that would be managed code, where if I compile something in C#, I have to have the .NET runtime libraries loaded on my machine. And that interprets how that code should run and then tells the operating system what instructions it should be dealing with. So when we're dealing with unmanaged code like C or C++, really all we can get back is the disassembly of that. So we can get the assembly code from it. If I'm dealing with managed code, typically we can reflect that back into its original source relatively easily. So just kind of based on how .NET and things like Java and stuff like that run, they need something to interpret that and then instruct the operating system.
Another question.
Yeah.
Maybe I'm getting ahead. Let's say I'm selling my .NET app and I don't want people to reverse engineer it. Can I encrypt it or something?
So yeah, that's a good question. So if you're selling, let's say, a C# .NET app, super cool, highly sought after piece of software, it's got a lot of great intellectual property in it. And I don't want somebody to be able to relatively easily reflect that back into the original source code. right? Because that's going to be damaging to my product that I'm trying to sell. Really, the things you have about that are obfuscation for it. There's a really interesting correlation between how malware is obfuscating itself and how companies protecting intellectual property are obfuscating their software. There's a huge overlap in that. I have a link I'll post, and I'll make a note of it here onto the GitHub that talks about some of the different obfuscation strategies for that. Companies selling the software to do that for you typically aren't real open about how it works, obviously to protect their own secret sauce.
There's no check mark in Visual Studio that says obfuscate my code.
There is not a check mark built in by default. There's a utility called Easy Obfuscator. It's just a thing you can pull off GitHub, build the solution, and it actually gives you like a little drag and drop window in Visual Studio, and you can drag your project file into it, and it'll obfuscate the whole thing for you. It's relatively good. So we can play around with that too, because the obfuscation stuff is really cool for kind of more difficult challenges for your students.
So usually malware would come in unmanaged code because it's harder to go back to the source code?
Typically, so the thing with like unmanaged code is you can bundle everything that you need for that piece of software to run on someone's machine. So if there's like external dependencies, you can statically link it, and that puts everything in that one binary file. You drop it on their machine and run it, and it's just going to execute. Problem with doing static linking, though, is you're pulling a lot more stuff into that piece of software, and it makes it larger, right? So if you have a very limited space that you can drop something, it's not always practical to do. So then you have to rely upon dynamic linking, which you make the assumption that their machine is going to have those dependencies on it. And for the same reason, you probably won't see malware. I shouldn't say you won't see it. Malware written in things like PowerShell or even your C# applications requires some level of .NET to be on that machine to run, right? So you're making an assumption that it's going to be on there. Modern Windows, it's a pretty safe assumption for that. Then you get into all sorts of weird, like a lot of the malware that we're seeing now is a mix of PowerShell delivered through like a malicious document or C# directly. And you can run C# from PowerShell and vice versa, so you can kind of intermix the languages, and it gets real weird, but that's kind of a trend that's out there. So go back to my philosophical question here for you. If I gave you a compiled binary, and it was a simple C program, compiled it, told you it was 32-bit, not that you need to know that, you disassembled it, could you give me back the original C source code? Like if you read that disassembly, understood exactly how that program was working, could you give me a line-by-line copy of my C code?
It's possible.
It's possible. I'm seeing some no's. Like,
So like structure-wise, it's very naming was.
okay, good, yeah. So structure-wise, let's say my C program counted from 1 to 10 and just printed out those numbers. If you looked at the disassembly of that and you saw this program's just printing out the numbers 1 through 10, you could write a C program and give me a functionally exact program. But what you probably won't be able to get is, like you said, the naming conventions. What did I call my variables? Did I use variables? Stuff like that. If we were going to write out a program that used loops, you don't know if I used a for loop or a while loop or a do while loop. When we compile that software, typically your assembler is going to look at how should this program work, find out the most efficient way to do that for your machine, and then output those really efficient instructions. So it's not always possible to get a line-by-line copy of the source code back, but that's not our job as reverse engineers. Like, nowhere in the history of malware have we tried to recreate the sample exactly how the original authors created it. What we really want to know, though, is how does this thing work? How is it spreading? What is it doing to the machine? We look for things like attribution. Could we figure out who wrote it or where did it come from? Stuff like that. So our job is to really understand how something is working, not necessarily the exact specifics of how it was created. And so I think that's like a really important message for like students to have as well. In the beginning, it's fun to give them exercises where you say, here's a simple C program. You can tell them all the compiler options and have them recreate that. But I don't think that's like the main goal of what we're going for in RE. So let's open up a tool here, just to kind of quick demo some of the problems and challenges that come up with that. I'll have you open up a browser, and we're going to open up a tool called Compiler Explorer. The URL for it's godbolt.org. Okay, so when you go there, a couple things I want you to do. So most of my demos and examples are going to be written in C. So in that first box on the left-hand side, make sure you change your language to C. And you can see there's all sorts of different languages that this tool supports. The right-hand pane is actually going to be the disassembly of your compiler output. So this tool will compile the programs, show you what the disassembly looks like on the fly, which is really handy so you don't have to write the software, save it, compile it, open up a different tool, decompile it, look at it. For kind of starting out, I really like to use this just to show some simple changes for that. So the compiler that I'm using here, underneath the compiler window here, is GCC 12.1, which is just the newest one that they have loaded up in the tool. And I wrote a very, very simple function here. Go ahead and write that function out for me. This is like the Hello World program before Hello World was cool. So it's nice to see on the left-hand side we have the C, right-hand side we have the assembly. When you look at this program, is this a 32-bit program or a 64-bit program? 64, good. What's your giveaway for that? The registers, right? So we see something like RBP, RSP. Those are going to be an indicator that it's 64-bit. So that extended register set. If it's 32-bit, we'd typically see what registers up here? ESP, EBP, EAX, all those types of things. Kind of a question for all of you. So knowing that software is generally all moving to 64-bit, right? It's actually really hard to find 32-bit software that is built natively for that. Is there value in teaching students 32-bit reverse engineering? What are your thoughts? So I see a lot of like yeses, like why should we teach students 32-bit?
Is the math is easier if you need to do math?
Like that's a legit answer. The numbers are just a little bit smaller, the math is easier. We can go through the same tools and the same processes, but sort of reduce the complexity of having giant numbers. Like if I asked you to add 10 plus 50, you can do that relatively easy in your head. If I ask you to add 1,500,429 plus 3,026, you could probably do it. It's just not as easy, right? It's the same process, just more complicated. Do we still see software that actually is 32-bit? Like if I have a 64-bit Windows machine, can it run 32-bit software? Yeah, like it's still there, it's still relevant. Just knowing that the trend is going 64-bit's important. But when we're starting out again, right, let's build a really strong foundation and then make it a little bit more complex. So what I want you to do here is we can actually change this to a 32-bit program if you just want to see the difference. If you know your GCC compiler flags, that would be a -M32. And there you can see basically the exact same program, just with those different registers that we have. We'll stop here for a little bit, go ahead and grab some coffee, walk around, do what you need to do, and we'll start at, we'll say 1032.